So this is still under chapter 1, superposition theorem, using superposition theorem in AC circuits. But before we dive into superposition theorem, first, this is the calculator, most calculator that is being used to set up your calculator into complex mode. So you need to press shift mode or mode or simply mode, then look for that number 2 here, then press 2, then you are now in complex mode. Now sometimes, most of the time actually, we want to be our output mainly in should be in polar form. So to set your calculator to be in polar form, uh, the output, so that you don't need to convert that one every time you have an answer, you convert it into polar form. So you can change the settings here, shift mode, then press number 3 here, press down the number 3, then complex results. So you choose what would you want to be your result when you press the equal sign in your calculator. So for us, we want to choose the polar form. So press number 2. So if you add, even if you add rectangular form complex numbers, when you press equals, the result will be in polar form. So now, this is your calculator. So let's go back to the superposition theorem. So again, just like the nodal analysis and mesh analysis, the concept is still the same as the concept in circuits 1. So when we say superposition, you have two or more sources. Then you want to calculate the effect in one component or parameters. Then you should remove first all the other sources, then compute for the effect of that one source remaining. Then you do that for every sources, and after that, you add them all algebraically based from their directions so that you can get the total effect. To illustrate this, let us again use our example from the previous discussion in mesh analysis. This example here, we can use this one so that we know the answer. We already know the answer. We can use superposition to calculate the answer again. But this time, we can just, because this is superposition, we don't use superposition to solve for all the branch currents. Superpositions are mainly used to solve specifically for one branch current or one parameter, just like Thevenin and Norton's theorem. Because it's very tedious if you want to solve for every branch current using this method. It's not practical to use superposition. So for example, here, instead of solving I1, I2, and I3, if I want to solve for I2, just I2, but you can still solve for I1 and I3. You can do that. But the concept is still the same. So, but in this example, we will be doing just for I2. Then you can practice solving for I1 and I3 later on. We already know the answer for I1 and I3, so it's good so that you have practiced in solving those branch currents. So the first step in applying superposition is we remove all the sources except one. So we have two sources here. So we can just remove the EB and we retain that EA. And we have Z1, or Z1 is negative J4, that's a capacitive. So let's draw here a capacitor. Then we have that voltage EA. So this is our EA. This is equal to 100 plus J10. Let's just write 100 plus J10. This is an AC source. Then at the middle, we have 3 plus J4. So we have a resistor. That's 3. Then plus J4, we have a inductive reactance or inductor, positive J4. And for the right side, we have a pure resistive, which is equal to 5. And we remove EB. We replace it with, if it has an internal impedance, we replace it with the internal impedance. But if it's not, doesn't have or given internal impedance, just replace it with the short circuit. For an ammeter, what we do for ammeter is the opposite. So we just make it an open circuit for or for voltage sources, we replace it with a short circuit. So this time here, after removing one or retaining one source, we can now calculate for the effect of that source in the parameter or the component that we want to solve on. So for example, we are solving for A2, I2. So we want to determine the effect of 100 plus J10 in this also in Z2 or 3 plus J4. So we can call this one I2 prime. We can call it prime for the first, the effect of 100 plus J10. Then this is just a simple series parallel combination circuit. So we have a total current. We can name it I total prime. Then we calculate for I2 prime. So to calculate I2 prime, we just need to use the current divider theorem. So what's the current divider theorem? The total current, which is IT prime, you just multiply it with the divider circuit. So here, we are solving for the current passing to 3 plus J4. So the numerator should be 5. That's the opposite impedance. Then we add 3 plus J4 plus 5. So that is 8 plus J4. And this is our I2 prime. Then the next thing we want to solve is the I total prime. And how do we solve for the I total prime? It's just equal to the voltage, total voltage, which is 100 plus J10. And we need to divide that with what? We need to divide it with the total impedance, because it's total voltage, total impedance, then that is just the total current. It's ohms law. So what is the total impedance? The total impedance is this G4 here, negative G4, is in series with the parallel combination of 5 and 3 plus J4. So we just add negative J4 with the parallel combination. So how do we take the parallel combination? We multiply, then we divide. So we multiply 5 and 3 plus J4, so 5 plus 3. 5 times 3 is 15, plus 5 times 4 is 20J. Then this is all over 5 plus 3J4, or that is 8 plus J4. So this is our I total prime. Then we multiply this with 5, 8 plus J4. And from here, we can use our calculator to solve for I2 prime. So we can input that to the calculator. So we have 100. So let's input that. 100 plus J10. J10 all over negative 4. J4, negative J4, plus the parallel combination, 15 plus J20, all over 8 plus J4. And this is our I total prime. We multiply it again with the divider, which is 5 all over 8 plus J4. 8 plus J4. And press equal, then you see our result is now in polar form. It's not in rectangular form, because we already changed the settings into polar form. So this is 15.116, 15.116 angle 26.87, 26.87 degrees. So this is the effect of 100 plus J10 on 3 plus J4. So after that, we repeat the process for the other source. So we can just copy the circuit, then change. We can change this. So this will be a short circuit. This is negative J4. Then we bring back the voltage here, which is 100 minus J5. 100 minus J5. Then we repeat the process. We solve again for I2, but this time instead of I2 prime, we use I2 double prime. And the total current will be this also. We can call it I total double prime. So to calculate again I2 double prime, this is just equal to the total current multiplied by a divider. So this time, the numerator should be the opposite, negative J4. Then we added 3 plus G4 plus negative J4. So plus G4 minus G4 is 0. So we have just 3. And again, for the total current, this is the voltage 100 minus J5 all over Z total, the total impedance. This time we have 5 in series with the parallel combination of the two, which is negative J4 multiplied by 3 plus J4, that's the numerator, all over the sum. The sum is 3. And you multiply this with negative J4 all over 3. We can again use the calculator to solve this. Use our calculator to calculate this. So this will be 100 minus J5 all over 5 plus the parallel combination. We have negative J4 multiplied by 3 plus J4 all over 3. Then the whole thing is I total double prime. He multiply it with the divider negative J4 all over 3. And this will be equal to 12.048. So I2 double prime 12.048 angle negative 71.701. 71, negative 71.701 degrees amps. Then to solve for the actual current I2, which is going downward, I2 prime is also going downward, so it's positive. I2 double prime also goes the same direction, so I2 therefore will be equal to I2 prime plus I2 double prime. So they are both positive because they have the same direction. So for example, I2 double prime goes to the opposite direction, then this should be I2 prime minus I2 double prime. But in our case, they have the same direction, so we just add them. So this will be 15.116 angle 26.87, then plus 12.048 angle negative 71.701. So I2 now will be equal to 15.116 angle 26.87 plus 12.048 angle negative 71.701. And this is equal to 17.87 angle. The angle is negative 14.94. Negative 14.94 amps. So this is now the current passing through Z2, 17.87 angle negative 14.94. So if we take our answer in mesh analysis, here for I2 we solve I2, and this is also equal to 17.87 angle negative 14.94. For nodal analysis, I2 is also equal to 17.87 angle negative 14.94. And this is superposition in AC circuit.